Right, so schedule. So this week basically is for working with your team to gather some data, not all of the data you need for your input modeling report, which is effectively the lab report for this week. So that input modeling report, there's a little more details online, but basically we have a short description of the system that you've picked and why you've picked it. So, there's observable lines or potential problems with X or Y that you'd like to investigate. It doesn't have to be very long, concise, just kind of clear there. But then if you were to model that system, then what inputs would you need to model? What outputs would you need to capture for validation? And then for eventually from your simulation for evaluating performance. And then for a subset of those inputs, show me that you do have the ability to capture data from that system. You don't have to capture new data. If you are analyzing a system that data has been archived that is appropriate for the project, then you can use that. That's fine. But you need to see that you can get some data from the system and do a little bit of input modeling like you practice on in that previous lab 8 from last week. Then next week and the week after that, look at the output analyzer in Arena, which is a tool that Arena has to try to give you some statistical tools to do a little more sophisticated things with outputs out of Arena. In reality, dumping your raw output out and then using a better tool like R or SPSS or Jump or MATLAB even may, ultimately be better. But for this class, the stuff that you get out of the output analyzer is fun. In fact, for this class, usually the confidence intervals are about all you need to make a compelling argument most of the time. But the output analyzer does allow you to do a few other things. And then finally, lab 10, advanced topics, we talk about things like batching and so on that are useful tools that for building more sophisticated models. And so then after that, then there's basically, I think, 2 weeks or so where there won't be a lab, but you can use that time to meet with your TA, to work with your group, and so on. So that's the outline there. Final project, input modeling report, that's the one that's due. This is a group submission. Now that I've put everybody into groups, I think in this class, I've got everybody in groups. Everybody's agreed. There were 2 groups that I had to do some manual moving around to make the numbers work. But I think both of those groups are all okay, and everybody else was fine to begin with. Now that you're all in your Canvas groups, then you should have access to this input modeling report as a group submission, which means that if one person from your group uploads it, you all get it. So only one person needs to upload this. And so you'll turn it in, much sooner than you'll turn your final project report. And then that gives me a chance to go through and say, yep, that looks plausible, or this seems a little too ambitious, or, well, doesn't this problem seem a little too obvious? Can you make it a little more interesting so that it actually looks like something you'd want to use a simulation to find out something new about, as opposed to just using a sim to demonstrate something you already know? So those are usually the feedback that I give. And so that's kind of all that we're saying here. Details about desired format and content are posted on Canvas in the assignment. And then there are some sample input modeling reports that are also posted on Canvas to give you an idea of what those look like. Other things, ICAs on their normal schedule. Homework H is now available. So question 1 was from lectures G1 and G2 and G3. So it's about input modeling. Question 2 will be from today, which is going to be about output validation. So these are very similar looking tests, but one is for one thing, another one is for another thing. So one is for getting the parameters right and the families right when you're programming your sim. The other one is for once your sim generates data, then to sort of say, is my simulation doing things that look realistic? And that's what we mean by output validation. So that's what we talked about today. And then the last homework, then homework J2, this is a special assignment that we use to capture some ABET metrics. So there won't be a solution set and you won't be able to drop it, but homework H and before, the lowest one of those is automatically dropped. So any questions about what's expected moving forward? Great. So for kicks, let's do a early iClicker here. I'll do poll. Whoa, that's not what I meant. I'll do. I want. I've never done this. I'm going to try one of these here that I've never done before. Um, Let me see if this works. All right, yeah, good. Um, so close the results for now. I think this multiple answer will work here. So choose the answer or answers that properly fill in these blanks. So based on what we talked about now, or our last week, I should be most suspicious of either low or high p-values when I have either a small or large number of samples. And so A is low p-values with small samples, B is high p-values with large samples, C is low p-values with large samples, and D is high p-values with small samples. So we talked about how, when we should be suspicious of p-values and how it relates to the amount of data that were collected. So what do you think? Go ahead and let's get that number going. And these are not graded for correctness. They're just kind of graded for coherence. And on these, then any answer you give is automatically coherent because you only have the four options. Don't choose E. I guess I could take away credit for E, but you know. All right, so looks like a lot of people have gotten answers in here. So if I get a really large p-value, I do a test. I do a goodness of fit test. I said I've got a model. My model is an exponential distribution, a Weibull distribution. It's a model of fair coin, so it's a 50% probability of coming up heads or tails. And from that, I sorry, just noticed something over here. Okay. And then from that, I look at my data and I run some sort of test, let's say a chi-squared test or a t-test, so to sort of try to validate, whether means are similar or whether distributions are similar. And I get a extremely large p-value, a p-value of 0.95. Um, Under what condition might I get a very large p-value and not be able to trust it? How do I get large p-values by default? And of course, it's related to data. So do you think I get a large p-value when I have large amounts of data or a large p-value when I have small amounts of data? Remember, the p-value is the probability of if the hypothesis is true, so if it really is an exponential, if it really is a uniform, if it really is the assumed distribution, then what's the probability that I would get data like these or more exotic data or data that are even farther from, say, the mean of the distribution? So a large p-value says that these data, given the data you've given me, these data are very likely to come from the distribution that you're asking me about. So when is that not informative? When you have lots of data or little data? That's the question. So if you have a high p-value, I either look at a high p-value and I say this is a good fit, or I look at it and say, no, I can't trust a high p-value because something to do with my data. Am I suspicious of high p-values? Are they a little sus when you have a large amount of data or a small amount of data? On Well, how many people? Well, I mean, I could look at the results here, maybe, but how many people are think you should be more suspicious of uh, high p-values when you have high amounts of data How many people think you should be suspicious of high p-values when you have low amounts of data? All right. So there's a little bit more of a tip towards low amounts of data. And that's what I'm looking for here, actually. So the idea here is that if you flip a coin once and it comes up heads, that gives you no information about whether it's a fair coin or not. So by default, if you flip a coin once and it just comes up heads, if you do a binomial test, it's going to have a high p-value for any uh, potential weighting, for any hypothetical weighting of that coin. You need to flip the coin many times in order for that p-value to gain meaning. So high p-values you do not trust if you have low amounts of data. If you go into Arena, like we'll mention here in a bit, and you say, hey, Arena, here's some data, show me the best distribution. And you're like, oh, wow, so the normal distribution with these parameters has a p-value of 0.76. That's pretty good. But if you only gave it 5 data points, then that's not actually that useful, because if you look at every distribution, the p-value is going to be way above 0.05. So low amounts of data give you high p-values. And then on the flip side of that, if you have really, really low p-values, that would normally mean you should reject the null hypothesis, because that's saying that it is very unlikely that the data that you have observed could have come from the purest form of this ideal distribution that you've given me. That's what a low p-value is. But if you have high amounts of data, then you're going to be able to detect a difference from an ideal distribution, even if that difference is minuscule. So if you gathered enough data about me, you could detect that my heart rate is slightly, is being affected by the orbit of Pluto around the sun. So if you gathered enough data, you would have to gather a lot of data, but I am sure that as Pluto spun around the sun, every time it hit certain points, you would see a slight variation in my heart rate. And you aha, Pluto is affecting your cardiovascular health. Well, that's not the right, just because your test detected a difference from a null model that didn't include Pluto doesn't mean that we should care about Pluto, because it's such a small difference that it's not meaningful. And so that's what, if you see really, really low p-values, so this should happen whenever you get a report or whatever. If you see someone has, p equals 1 times 10 to the negative 15th, then you should look at that and say, how much data did they gather? And if they gather millions of samples, then it might be that that p-value just means that they've managed to detect a really small difference. So then your next question to them is, how big was the difference you detected? What was the average value of the data that you gathered relative to the average value of the null expectation you were testing against? And if they're not that different, then you can say, well, yeah, you detected a small difference, but it's so small that it's not meaningful in any practical engineering sense. So you have to be really careful about extreme p-values. You can't interpret p-values without also doing a gut check about the number of samples. So the answers I was looking here are low values, be suspicious of when there's small data, small amounts of samples, and high p-values, be suspicious of when there's large amounts. So I was looking for A and B. So any questions about that? Okay. Go ahead and stop that one. Okay, so let's do one more. A statistical, so maybe I'll just give you this one. And so we won't have to do this one, because I don't think I'm going to talk about this a lot more today. But if I recall on Thursday, I didn't actually say this very often. But the term that we use, a statistical test with higher statistical power, will reject a false hypothesis with fewer samples. And so you can have tests that are more sensitive. So in general, the more data you give me, eventually my test will detect a difference from null, even if it's not a meaningful difference. But some tests can do that with less data than others. The ones that can do that with less data, we say are higher powered. So in this class and in any class that revolves around statistics, that you will start hearing the word power. This is what power means. It means it is a test that is very sensitive, that can detect small differences with small amounts of data. That's what we mean by statistical power. All right, so we'll see that more. Just some other terminology here. We're going to be using the terminology that a positive effect is when or a positive outcome is when we detect a difference from null. So it sounds a little, it can sound a little weird. We have a null hypothesis. And so when we detect a difference, we say that's positive. So, and the reason that that's kind of positive is that the null is something we're sort of assuming to be the case, for better or for worse. For goodness of fit, it's for better. For a lot of other cases, it's for worse. And we use a statistical test because we want to see, is it different from the assumption? So if we've managed to detect a difference, that's, I guess, a good thing, which is why we say it's a positive outcome. So a positive is to detect a difference from null. The alpha, we're going to call the significance level. We're also going to call the risk of type 1 error. And we're also going to call the false positive rate, or FPR. So all of those are synonyms for each other. They mean exactly the same thing. So like we talked about last time, an alpha equals 0 means you don't reject anything. An alpha equals 1 means you reject everything. So alpha equals 0, the way you don't reject anything is you just make infinite critical values in your chi-squared and your t-test, whatever. Alpha equals 1, you set all those critical values to the lowest value possible so that everything triggers them. And then, yeah, like I said, the p-value, the probability of an observed deviation, so a positive effect, I guess, but I don't want to say that here because there's no threshold when we just talk about p-values, but the probability of an observed deviation if we assume the hypothesis is true. So the significance level gives us that threshold where we'd say that when the p-value is less than that threshold, then we've detected a difference. When it's greater than the threshold, then we're not willing to say that we've detected a difference. All right, so that's just review. So any questions about those terms? Everybody on board with that? Okay, so remember, it's positive to detect a difference. So the other error, beta, this is our type 2 error. That's the probability of not rejecting a false hypothesis. So when the null is false, which the book says, the book will talk about the null H naught or H null, and it'll talk about H1 as an alternative hypothesis. So sometimes the book will say when the alternative is true, that's a synonym for saying the null is false. So it's a little safer, I think, to say the null is false. So when the null is false, then under that assumption, given the data we have, and the test we have, then the beta, which is a measure of the test, is what's the probability that we fail to, I don't want to say detect, but we fail to reject the null, even when the null is actually false. So that's what we mean by type 2 error. It's the other half of it. So this is sometimes known as FNR, false negative rate. So this is a negative error. The other one is a positive error, alpha and beta. So that's what we get with those. And then statistical power, the term I just talked about, is just the complement of type 2 error. So a highly sensitive test has a very low type 2 error. So if you have high statistical power, you have low type 2 error, you have low beta. So it's just often easier for us to talk about statistical power. And so we do the 1 minus, and so we talk about power. So we talk about a high powered test. Well, that's no different than saying a test with low type 2 error. They're equivalent terms, but it's just often more convenient to use the power language than the error language. So sometimes this is also called sensitivity or true positive rate, TPR. And so what determines a test power? Well, part of it is the variability. So if you have data that could be anywhere, then the test is going to have a harder time detecting, differences. If you have two distributions that both have high variance and you're trying to detect a difference in mean between them, that variability is going to make it challenging to find small differences in the mean between these two distributions. And then the number of samples. If you have few samples, then that also is going to make it harder for that test to detect a difference. So a higher power, it means that the test can, with fewer samples, can cope with more variability. So you are going to do in the second part of the homework a power analysis, which is a tool that we use to determine that for the variability that we see in the data, how many samples do we need to get an appropriate power? But we also have to put in how small of a difference that we care about detecting. So in the Pluto case, that would be such a small difference that would have to be kind of lower than our threshold that we care about. So you have to sort of say, I want to be able to detect important differences. So in a power analysis, you have to say, well, what is an important difference? Well, an important difference would be like a change in heart rate of more than 10% or something like that. So I don't care about any effects that reduce my or that change my heart rate by less than 10%. There may be a real effect. I don't care if your test detects it. I just don't care. And so given that I need to only detect 10% or higher, and given that there's this much natural variability in heart rate, then how many samples of the heart do I need to take in order to be able to detect that 10% deviation? That is what a power analysis does, and that's what you'll get practice doing in the second part of the homework. So any questions about this? Statistical power, power analysis, where this all comes from? Okay. So then that brings up the ROC, so the receiver operating characteristic. So this was a curve that is now used a lot in machine learning and data science. It was actually started out when the receiver, this was a radar receiver, this is a person who would be looking at data from radar, and I think it also applied to sonar. So people listening to active sonar pings and submarines and things like that, and then seeing how well they could detect real objects versus just spurious objects that show up. And so they could measure people's type 1 error, their false positive rate. So how often did they say, oh, that's a ship, and it turns out it's not. And then they could measure their true positive rate. So how often when there was a ship did they actually get it right? So there's basically statistical power on one axis, false positive rate on the other axis. And if you just flip a coin that comes up as a detection with alpha probability, then so it has no relationship to the data. It's either 0% of the time it comes up heads, 100% of the times it comes up heads, or 50% of the time it's back and forth. Then you walk right along this diagonal line. So if your statistical test fits on this diagonal line, it's no different than a coin. So you don't want your statistical test to fit on this line. You don't want a receiver, a human that's trying to decide, oh, there's a ship there, there's not, to sit on that line, because that means you could replace them with a coin. But these lines here represent three different statistical tests. So for the same data, people piped these in and they gave them different alpha thresholds. So just like with a t-test, you could give it a different alpha threshold, and so you get different classifications. So it would make different decisions based on different alphas for the same data. You can do that for three different tests for the same data. And then you can plot out how does the false positive rate change and how does the true positive rate change. And a really good statistical test will bow as far out here as possible. And a kind of bad statistical test will be close to this diagonal line. So this difference between here is something that people will quantify. They'll take the area underneath that, and that it's the AUC, the area underneath the curve. So a lot of times when you see people designing new the decision classifiers, then you'll see them list the ROC AUC, which is the area underneath the ROC curve, the area underneath the curve of the ROC curve. So but what the And so that's just sort of because you're going to start seeing those as if you get into more data science and so on. But the key thing that I want you to be taking out of this at this level for this class is that there is a trade-off, a fundamental trade-off between false positive rate, type 1 error, and true positive rate. So as you increase the false positive rate, you also increase the true positive rate. To put that another way, as you decrease your type 1 error, you'll increase your type 2 error and vice versa. So there is no so-called Pareto improvement. There's no way to improve both simultaneously. You're stuck with this trade-off. So if you want, and that's what we kind of talked about before, is that if you really don't like type 1 error, you can squeeze that thing down, but you're then going to get a bunch of type 2 error. And so the way you're getting fewer false positives, the way you're getting fewer rejections is you're basically losing out on a bunch of true rejections. And so you're pushing error from this axis onto that axis. So those two, don't think of alpha and beta as independent. They are coupled together. So any questions about this? And that trade-off even happens for flipping a coin. That diagonal line is just flipping a coin. It's, unfair coin tails, unfair coin heads, fair coin right in the middle, everything in between. And it still has this trade-off between FPR and TPR. Okay. All right, so so last time we talked about summary statistics. So hopefully that was a bunch of review. We have summary statistics for continuous, for discrete, and then for sort of the in-between histogram data. Big thing in all of these is that if you're calculating variance by hand, if you're using the mean that you've calculated in the variance formula, so you don't know the true mean, make sure you divide by n-1. If tools like Excel automatically do this for you. If you don't want them to use n-1, you have to pass them an additional flag to say actually divide by n. And that prevents you from getting bias in your variance estimate. And we talked about that we don't just want to know summary statistics, though. We want to know parameters for distributions that we've picked. And so one of the ways that we use the do for that is maximum likelihood estimation. Now, I did a contrast there because I said, let's say you estimate the mean and variance of I'll go to a discrete here, the mean and variance of a Poisson, of a likely Poisson. For a Poisson distribution, the mean and variance should be identical. But if you estimated the mean and variance from data, they won't be, because what's hidden here is that whenever you estimate a parameter, the real parameter will be nearby. So there's actually a confidence interval that 95% of the time captures the real parameter. But at this point in the class, we haven't talked about confidence intervals yet. And so this point estimate we take as our surrogate for the real parameter, but the real parameter is not likely this right here. This is just close to it. Likewise, this one is close to it. So these two can be very far from each other because the real parameter is in their mutual overlap. So if you were fitting a Poisson to data, then you're saying, well, which parameter do I use? The Poisson's alpha, its parameter should be equal to variance, but it also should be equal to mean. Which one? So that's where this maximum likelihood estimate comes into play, is to say, well, what we're actually going to do is we're going to take the probability density function or the probability mass function, we're going to load in the data as if they're parameters, and then we're going to treat the parameters of that distribution as variables, and then use a little calculus to maximize the density or the probability mass given those data across the space of all of the parameters. And that will spit out parameters that are, in the maximum likelihood sense, a best fit for the data that we have. And so if you do that for a wide variety of distributions, you get these nice formulas that normally the formulas have the sample statistics in them. And oftentimes it's sort of, they kind of make sense. And in which case it says, well, why did I go through that maximum likelihood estimate? Well, like he said, for the Poisson here, this is telling you that although theoretically the variance would have been a parameter you could have used to plug into your Poisson, actually the maximum likelihood estimator is the sample mean. So use the sample mean instead. So this resolves that ambiguity for the Poisson. So that's, and then if you look up more exotic distributions, like again, go to Wikipedia, look up any distribution you like, down the right-hand side, it'll have a bunch of useful formulas. And one of them will be the maximum likelihood estimator. And for some of the more exotic distributions, this is going to be a complex formula involving summary statistics and maybe some other things. So it's not always a drop in like, oh, well, I'll just set the mean equal to the sample mean. It just happens to work out that way for these kind of nice, clean, simple distributions. All right, so that's maximum likelihood estimation. Any questions about MLE? Hopefully that again is review. I think that we cover that in 380. And so what we didn't cover last time, what we needed to in order for you to do that homework is goodness of fit, which we've done a little bit before the midterm just for uniform distributions for our pseudo-random number generators, but we need to do that for generic distributions. And so goodness of fit is useful in two cases, input modeling. So I really think my arrival rate should be have exponential inter-arrivals. So what is the best rate that I would pick? Well, I'm going to pick an exponential, and I'm going to pick the best rate for the data that I have. That's for input modeling. Alternatively, output validation, I run my sim, it generates wait times. And so those wait times are not inputs. So when you do your input modeling report and submit that on Sunday, do not fit models to waiting data, to queuing data, to data that are outputs to the system. I will put big red marks through that. So, those are not for you to fit things to. Those are for you to compare to your sim after you've built it. And so your sim will generate a bunch of random variation. You'll have random variation from the real world, and then you can look at them and use a goodness of fit test to say, does the random variation that comes out of my sim look like random variation that matches the real world? And if it does, then great, my sim is validated. It's producing similar data that the real world is. So I can now use the sim as a surrogate for the real world. I can play with things in the sim and assume that I'm playing with things that would actually have a similar effect in the real world. So those are two ways we use goodness of fit: to estimate parameters and then to validate the output. So notice the key difference in application is in the input modeling case, I don't know the parameters and I estimate them from data. In the output validation case, I give parameters, and I say that, how good are these parameters? So, this is the parameters are given. That's a little bit like, well, this is the sim. It's just, it is what it is. How good does the sim match the real world? Remember this because there is a question on the homework which relates directly to this. It requires you to write some stuff out. And so that answer is embedded in here. Okay, and then this is just what we started with. Correct distributions are elusive or non-existent in real applications. You'll never have a correct distribution. You just have to find one that has a good enough fit. Very little data will give you high p-values. Very high data will give you low p-values. And so don't depend too much on p-values. So if you don't depend on too much of p-values, then what else do we use? And that's things like r-squared. There are a bunch of other metrics that we're going to see. But before we get there, let's then, stay with us, start with the statistical tests here. So, the goodness of fit tests you typically use are going to be based on counts. So we're trying to fit distributions. So how do we tell if a distribution matches? We're going to count up how often our real data falls into bins, and then we're going to compare those to expected counts if that distribution was the true distribution. And going into a statistical field, whenever you hear count, you should think of just immediately a synapse should fire and certain statistical tests should pop up in your head. And one of them that should pop up into your head is the chi-squared test, which will be what is next. The other one that should pop up in your head is the Kolmogorov-Smirnov test, which will be what we did talk about after that. Outside of the scope of this class, but if you go on to do a little more data science, something called Poisson regression. Remember Poisson, that's a discrete random variable which models count data. Well, when you get into more sophisticated data analysis, you end up fitting lines that relate to parameters of Poisson distributions. That's a more sophisticated way of handling count data. But those are the things that your brain should just immediately, oh, you've got count data? Well, I'm going to use one of these three tests. I'm going to use a chi-square test, a KS test, or Poisson regression. For this class, it's just the first two, chi-squared and KS. So how do we modify the chi-squared test that you've already used? This is, again, stuff that should be review. But we've already done this before the midterm, but we did it only with uniform. The key thing now is how we calculate the expected frequencies. So we can count observables in bins, and then we need to figure out how to do expected tiers. The other thing that we're going to be doing, and we're going to talk more about this in just a second, is that before I just said your expected counts have to be 5 or greater, and if they're not, then there's nothing you can do. Now, after the midterm, we combine bins, and this is what you'll do on your homework. You're going to get expected counts in your homework problems that are going to have less than 5. So what you do is you group those bins with bins next to them, making the bin larger, and that will then put those counts together, and you do that until you have 5 or more in that bin. And you try to choose combinations of bins that make sure you have the maximum number of bins as possible, because you want high degrees of freedom such that all of your bins have 5 or more. So you're kind of doing this like, I need all of the expected counts to be greater than 5, but I don't need them to be a lot greater than 5. So you combine all of those together. There are other ways to deal with when your expected counts are less than 5. They're outside of the scope of this class, and they're not very good anyway. So in this class, then you just combine these bins together, and that's what you'll do on the homework. Or if you have very little amount of data, and the only way you can combine the bins together to get this is to basically have almost no bins, like 1 or 2 bins, then you have to resort to the KS test, which we'll talk about here in a second. And then the critical value, like I've been trying to communicate, is a metric for the maximum allowable deviation from the distribution that you're evaluating how good that the data are matched to. And so before the midterm, we just said that in order to look up this critical value in the table, you needed to know the degrees of freedom, which were the number of bins minus 1. After the midterm, now we have this extra penalty, which is the number of parameters estimated from data. So in order for you to generate these expected counts, if that required you to fill into this probability distribution a mean or a standard deviation that you got from data, then each one of those that you got from data reduces your number of degrees of freedom. That's what I'll talk about here. So it's this idea that because if you know the sum of a bunch of data, like so here I know that I've got in bins, and if I add all of those counts together, I get the total number of data. That's the reason you lose 1 degree of freedom. Because if you know that I had 100 samples and I know how many were in all of the n-1 bins, I immediately know how many are in the last bin. So I don't actually have real data that are in that last bin. It's just sort of throwaway count data. That's why there's only n-1 degrees of freedom. There's only n-1 dimensions that can vary independently from each other. That's what I mean by degrees of freedom. That gets worse when you estimate parameters. So if in order for you to calculate the expected counts, you have to calculate a mean to plug into that distribution, you're going to set up another one of these simplexes. You're going to set up another one of these things where you're going to say, well, I know the mean is this. I calculated it. It was a function of all these data. Well, that means that if you knew the mean and you knew all but n-1 of those data, you could solve for the other one. So every time you estimate a parameter, you're actually adding kind of another equation, that you're basically replacing a data point with a parameter. So if you had to estimate the mean, you lost a bin, basically. If you had to estimate the variance, you lost another bin. So you're swapping out bins for parameters. And that's the reason why the total degrees of freedom for a chi-squared test is you start with the total number of bins, you subtract 1 because they have to add up to the total number of samples, and then you subtract however many estimated parameters, because each one of those loses an independent degree of freedom as well. So that's where that comes from. So if eventually you subtract away and the degree of freedom comes down to be equal to zero, then that basically means that you've turned all of your data into parameters and there's no degrees of freedom left. You just may as well not do the test anymore, because the only way you could get those parameters is from those data points. You've just, that, so there's nothing, there's no distribution left. It's just a single point. So that's what it means to have a degree of freedom equal to zero. Okay. So questions about this, about what we mean by degrees of freedom, and then subtracting one and then subtracting off S. All right, so these are examples of that. If I'm evaluating whether data are normally distributed and the mean and standard deviation are estimated from the data, then for the chi-squared, I take the number of bins I chose minus one, minus the two parameters that I estimated. And so in this particular case, if I started with, 5, then I end up with 2 coming out of here. Alternatively, if someone says, hypothetically speaking, these data are normally distributed with a mean of 5 and a variance of 2. The 5 and 2 did not come from the data. They came from the hypothesis. Somebody said, hypothetically, this is where I think the data should be. In that case, those parameters were not estimated. I do not lose degrees of freedom. So in that case, I just subtract 1 from the number of bins. So I don't penalize for parameters. The one special case for this are a couple of these weird parameters for like the uniform, the triangular distribution. If the parameter is not arithmetically coupled to the data, then you don't lose a degree of freedom. So if you look at your data and you say, I'm actually going to assume that my hypothetical uniform goes from the minimum data point to the maximum data point, I don't actually lose any degrees of freedom, because I'm just kind of picking those kind of arbitrary. Like I could have picked them for the minimum -1 and the maximum +1. They're not arithmetically, they're not directly coupled. So there's a few of these parameters that don't penalize you, but all the parameters that I'm going to ask you to do calculations about are going to be the ones that penalize you. So you don't have to worry too much about me throwing a trick question, because I don't see the value of that. But I do want you to know that if you do have to, if somebody does give you he says, well, test to see if they're uniformly distributed. And you say, well, between what? And you say, I don't know, look at the data. Well, if that's the case, then the bounds that you pick do not actually kill any degrees of freedom, like solving for a sample mean. Any questions about those examples? You see what I mean by penalizing parameters? All right, so you'll have an opportunity to do this on the homework. So this was the example we had pre-midterm, give you a bunch of data, put into 4 bins, count how many go into each bin, and then calculate the expected number of observations in each class. Well, given that it's a uniform, then I know it's just going to be the number of data points divided by the number of bins, and that's greater than 5. Great, so I can go forward and do my chi-squared, just like we did before the midterm. Now, after the midterm, we have to calculate this. So how do we do that? Well, all we need to do is calculate the probability that data would land in that bin, assuming the distribution that we're testing for. So if you're testing for a Poisson distribution, then you say, all right, well, I'm going to add up in this bin goes from 0 outcomes to 6 outcomes. Well, then I'm going to add up the probability mass for 0, 1, 2, 3, 4, 5, and 6. Add all those together, and then that becomes the probability that it's fallen into this 0 to 6 bin. Once you have that probability, then you multiply it by the total number of sample points, and that gives you the expected number that are going to go in that bin. So for a discrete random variable, you ask how many discrete outcomes fall in the bin, and then you find the probability for each one of those outcomes, sum them all together. That's what gives you this probability multiplied by the total number of samples. That's your expected count for the bin. For continuous, you have to integrate over that interval. And usually, if it's just a nice simple interval like these, it's not broken up into multiple pieces, then it's just integrating from the low end of the interval to the high end of the interval. And if I give you the CDF, then you just evaluate the CDF at the high end minus the CDF at the low end, and that's what gives you that probability. Then multiply it by the total number of samples, and you're good. So, I mean, kind of the summary here is, and that's what I'm sort of saying here for this continuous variable, is that if you're saying, well, this is my size of the bin, then if I'm given the CDF, it's pretty easy to calculate the probability that you fall into that bin, and then just remember to scale it by the total number of samples. And so that's, so any questions about how to do that then? Says you will do this on the homework. So you're just figuring out the probability that outcomes fall in the bin multiplied by the total number of samples. And then that gives you a different amount that'll fall in every bin as opposed to the uniform where it was the same. If that number is less than 5, then combine it with the next smallest bin around it. And then with that one, redo this calculation. If that is still less than 5, keep doing that until eventually the expected number is 5 or greater. Questions about that? Again, hopefully review. Okay, so just, simple example here. X is hypothesized to be exponentially distributed with a given mean. I've bin observations into 10 subintervals. So then for the chi-squared test, should the degree of freedom be 10, 9, or 8? So how many people think the degree of freedom here should be 10? I started with 10 intervals, so the degree of freedom might be 10. How many people think it should be 9? I started with 10 intervals, so the degree of freedom should be 9. How many people think it should be 8? Nobody. We've all tuned out. So let's focus and try it one more time. So 10 subintervals. So I've got exponentially distributed. I got a bunch of data. It's going from 0 to very large. And so I decide to chop it up into 10 intervals, 0 to 1, 1 to 2, all the way up to eventually one that's like 9 to infinity. That's my biggest bin. And so I got all those bins. I got counts in each one of those bins. And I'm going to use a chi-squared test to evaluate whether these counts are the counts that I would expect if it was exponentially distributed with a given mean, a mean that is not determined from the data. So I've got 10 bins. It's a chi-squared test. I need to look up my critical value in the back of the book. So is my critical value, how many people says my degree of freedom for my critical value, I look up in the back of the book, should be 10 for this one? How many people say it should be 9? Okay. How many people say it should be 8? All right, so it looks like most people said 9, and that's the answer that I'm looking for here. So the reason it's 9 and not 8 is because that was given. That is not dependent on the data. If I would have said it's hypothetically exponentially distributed, you just find the best mean from the data, then it would be 8. So any questions about that? Okay. So that's just kind of showing this here. So if I say I want the interval to go from 2 to 3, then I am going to look up the CDF for an exponential, evaluate it at 3 and at 2. It gets about 14.5%. I'm going to multiply that by my in observations. And so that will give me the expected number of observations in this interval. And I would do that for all 10 of my intervals. And if one of those intervals has an expected value that is less than 5, I find the interval nearest to it that has also a low, that has the lowest. Like the one nearest to it might actually be fine. It might have an expected value that's a little bit higher than 5, but just because I want to combine them when they're next to each other, then I just have to add it to it. And so even though that one was okay already, because this one wasn't, and I know other options, I have to group it with the one that was okay. And that's an example you might see on your homework as well. Any questions about this? Okay, great. All right, so what if this is impossible to get over a large number of your bins, that things will be less than 5? Then we go like before the midterm to the KS test. We sort all the numbers, we don't bin, we do it all by sorting instead. And so the KS test can be used as a goodness of fit test This is a one sample test. That's a difference between a hypothetical distribution and your data. It can also be used as a two sample test, which is sometimes known as a test of independence. That's when you have two data sets and you want to ask, do these data sets come from the same distribution? So, a lot of times this would be like, this is a data set I got for people at, when this is heart rates for a room that is 20 degrees Celsius. And this is heart rates for a room that is 30 degrees Celsius. And I get a distribution of heart rates in both cases. And I want to see, does temperature have an effect on heart rate? Well, if it does have an effect on heart rate, then these two distributions, the KS test, will detect that they don't come from the same distribution. If temperature does not have an effect, the KS test will fail to detect that, and it'll be as if you could just pool those things together. It'd be like the same distribution. So that's what we mean by a two sample goodness of fit test, or a two sample independence test, or the one sample. So in this class, we are going to typically be focusing on this one sample, but you can use the KS for this two sample as well, as you can in the chi-squared. So the KS test is useful when sample sizes are small and when no parameters have been estimated from data. You cannot use a KS test. Well, there are a couple of custom-built KS tests for certain distributions that have parameters that are estimated, but it's not like the chi-squared where it's a general purpose test in that case. The KS test is only general purpose if no parameters have been estimated from data. But when you get that far, if these conditions are met, it's much more powerful. So with very little data, you can still detect a difference from a distribution. So I only have 10 samples. If the KS test said those 10 samples aren't normally distributed, they're not normally distributed. It is a powerful test. Whereas the chi-squared test probably won't be able to detect that difference. So how does it work? We saw this before the midterm. If this is my sample CDF and this is my approximate CDF for a uniform distribution, the KS test basically measures the difference between where the data actually fell and where they should fall if they were going along this distribution. So before the midterm, you basically sorted all your data, put them into the middle row here. You calculated saying that if this was uniformly distributed, then this data point should fall between 0 and 0.2. Likewise, this one between 0.2 and 0.4, and so on. And then you calculate the differences, take the largest difference, and that's your KS statistic. How do you change this for an arbitrary distribution? You pretty much do the exact same thing, except the data that you're going to put in this middle row are your data passed through its own hypothesized CDF. So these data points could be anything. They don't have to be from 0 to 1. But when you say, I'm testing to see if it's an exponential, if you put the exponential CDF in here and plot the data through the exponential CDF, that CDF will be between 0 and 1. And the crazy thing about it is that when you do that little transformation, typing the data through the CDF, if it's the right CDF, or in other words, if the CDF agrees with the data, then the points you get out of that little mapping will be uniformly distributed. It's sort of like the inverse transform sampling in reverse. So, but when inverse transform sampling, we drew uniform, piped in the inverse, and we got whatever we wanted. This is going the other thing where we have something. If we chose the right CDF, if we pop it into the CDF, we'll get uniform out. It's exactly the reverse of the inverse transform method. And so then you do the test exactly as you did before the midterm. Simple. This is the way that would look graphically. So here's your sample CDF, that's the black one. And then this blue line, that's your hypothesized CDF. So this is what the CDF is for an exponential. So you can imagine plotting it and then seeing do these fall in the right ranges. The alternative way I could have done it is to, instead of plotting the sorted data, I could have plotted their CDF transformed versions, and then this would look just like this over here. All right, so that's the modification of a KS. It's basically identical to pre-midterm, but you just do this transformation on the data first. Any questions about that? So use the KS when you can't get a significant number of bins that have 5 or greater in them and the expected value with the chi-squared. Don't use the KS for large amounts of data because it will just reject everything because it's so powerful. And that's all I'm sort of saying here. I'm just going to skip ahead just for time here. There are other tests that you'll see. The book mentions the Anderson-Darling test. This is also a very powerful goodness of fit test. It has its own pros and cons. So if you see Anderson-Darling, just know that it's a powerful goodness of fit test. I'm not going to ask you to use it, but I just want you to hear about the term. A more commonly used term, at least in the sciences in particular, for sure, is the tests that are specific to certain distributions. So as you'll find, a huge number of so-called parametric tests require your data to be normally distributed before you can even use that test, like the t-test. You can't actually use a t-test unless your data have been confirmed to be normally distributed going into it. So you need a high-powered goodness of fit test just for normality, and that's the so-called Shapiro-Wilk test. So if you have a bunch of data and you're like, I don't know if I can use my t-test or not, then the way you do it in the way you can convincingly use a t-test or an ANOVA or all these other tests that require normality is you'd say, even if you have a small amount of data, you have to justify to your reader, to your audience, that those data are normally distributed. And that's why we have a super high powered test that only tests for normality. That's the only thing it does. But because it's focused on normality, it gets a huge amount of power. So that's why we have the Shapiro-Wilk test. So I'm not going to ask you to do the Shapiro-Wilk test, but we will be using parametric tests in this class. We will be often assuming that things are normally distributed, and we have good reasons to assume that. But when you leave this test, if you go to your boss and say, hey, boss, I tested this with a t-test and XYZ, your boss will expect you to have checked for normality before you did that parametric test. So you should know that these tests exist, because you'll get in trouble if you use all the tests that you learned how to use in 380. You can't use unless you use this test, which you probably didn't learn in 380 or 385 beforehand. So know that it exists, but I'm not going to require you to do it for time. And then, yeah, this is just what I've been talking about. That p-value can be a weak measure of fit. So as we'll see, ARENA does not only give you p-values, it's going to give you r-squared, so the squared error. That combined with a p-value can be very informative. In later classes on model selection that you might take, or just later lifelong learning that we all have to do as engineers, you'll learn that sophisticated ways of sorting models by fit use these things like AIC. This is outside of the scope of the class, but this is a metric which takes the r-squared and penalizes it based on the number of parameters in the model. So you not only are sorting them by how well they fit, but if they use a lot of parameters, then even if they fit well, they'll actually be very low in the list. So if they use very few parameters and fit well, then they come up high in the list. And that's what these sorts of metrics do. Outside of the scope of this class, but again, in reality, as you start doing so-called model selection, then you're going to see this pop up, this term, and that's basically just a modification of r-squared for the number of parameters. And then, of course, QQ plots and PP plots, these are still used. So if you are convinced that you have a good fitting family, just throw up a QQ plot and a PP plot, just so it just makes all of these numbers down here sometimes just don't, they just don't have a lot of oomph to them. But if you combine them with a good, QQ plot and PP plot showing linearity, then people start really believing you that you picked a good model. You'll in lab 8, there's this input analyzer. It does the chi-squared test and the k-squared test for you. It gives you summary statistics. It does the histogram for you and tells you stats about the histogram. So you guys know all of this by now. The one thing I do want to highlight is that very often your chi-squared and ks test will have different results. The chi-squared test, maybe in this case, fails to reject this for these data that they're triangular, and they look pretty triangular to me, but the KS test definitely rejects that, says, this is not triangular. The reason for that is because the KS test is a high-powered test, and we put a lot of data into a high-powered test. If you put a lot of data into a high-powered test, it's going to reject it. It's just going to happen. That's what high-powered tests are for. KS tests are for when you can't use a chi-squared because you have too little data. Once you have a lot of data, it's just useless even to bother calculating it because it'll always reject. And I don't think that should be rejected. So any questions about any of that? Okay. All right. So let's we're probably going to end up covering a little bit of this as in the next one here, so that we're kind of catching up to the lag from last week. But that's okay. This is stuff that we've talked about before about garbage in, garbage out, but now we're adding a couple of extra terms here. So we've got verification, validation, and calibration. So this is V and V is verification and validation is the kind of the code word here in the industry. Verification is largely, did I implement it correctly? So I wanted this to be an exponential, but I actually typed in tria when I was putting in my input models. That's on me. That's a coding mistake. So verifying you don't have any coding mistakes, that's what verification is. Given that, then I've implemented it correctly. Validation is saying, all right, was it actually a good idea for me to use an exponential? So it's at a higher level. It's not at the level of coding. It's at the level of, is it a good model? Was this good that this was exponentially distributed? Was it good that I had such a simple model here? So validation, do the outputs that come out of this, do they look like the outputs in the real world? The process of then using differences from the real world in this model to fix the model is the process of calibration, or improving the caliber of a model. So that's how we use those terms there. Did you verify it? That means, are there any bugs? Okay, then you can say, and I also validated that this is a good model. That means I went out and I looked at real world data, and my data looked like real world data. And then you could say, but there's some room for improvement. And so I calibrated it to be a better fit to the real world data. And that might have required you to add something in here, or that might have required you just to update a parameter or so on. So that's the three terms that we're going to use here. So overall, the process of doing this is something called TV&V, testing, verification, and validation. And this is sort of the flow chart of what I was just kind of talking about here. And then calibration, this kind of iterative process of making the model better and better. So any questions about those three terms, the difference between those terms, verification, validation, and calibration? And then V&V, you do V&V during the process of testing. So the buzzword you hear is TV&V. So has it gone through TV&V yet? Has it gone through testing, verification, validation yet? And then the TV&V people will say, yeah, it came through, it's crap. And then you can say, okay, well, I'll fix it. And so maybe it's not crap anymore. So then you go back and forth, and that's calibration. Okay. So I don't want to spend too much time on this. I think it's pretty clear. It's example, modeling a bank. And so like you might do for your input models. And so I'm going to build this model. But before I build it, I know that I'm going to measure these things on the output. I'm going to have these things on the input. And these are the things I'm going to vary inside my system. So in other words, these are my input variables. So these are the input modeling. These are the things that, so in your input modeling report, you should highlight these things and say, these are my inputs. And hopefully then have some data to fit some of them. And then the outputs here, these are the things that I'm also measuring or going to measure, but I'm not fitting models to. I'm measuring them because I need to evaluate, I need to validate my model. I need to see if my simulated model generates a similar average delay as the real world model. And these are also the things I'm just generally going to take performance over so that I can optimize my decision variables. So that if I want to say I want to reduce the average delay in my bank, well, how am I going to do that? Well, these are my degrees of freedom for my design problem, my decision variables. And so I'm going to train my employees to have a lower service time, or I'm going to add a line, or I'm going to add a teller, or so on and so forth. So how do I optimize over this space, this decision space, to make these better. So that's the other thing that I do with these output modeling. So this is going to be an example in output validation. So I collect my system response and then from my real world, and then I collect the model response from my sim. I ensure that all data is collected during the same time period, so I'm not accidentally comparing Monday at noon in the real world to Saturday at 7 a.m. in the sim. And then I compare the outputs from these two. I am going to take the approach where I'm going to just average. So let's say I'm just focused on Y2, which in this case is average delay. So I'm going to say that in the real world, the average delay, the average delay is 4.3 minutes. So let's look at my outputs and then test the hypothesis that my outputs have an average equal to this one. So next time, we'll then say that now that we've set up Gesundheit, this hypothesis to test, how do we then choose a statistical test, run it, and see if we have enough data doing that power analysis that you're going to be doing on the second half of the homework. But I don't want to keep any longer than that, so let me get to a clicker so that we can get you out of here, there, and lost my little clicker guy. Okay, so the short answer here is, what is the word we use for verifying that you've coded your model correctly? So that you've built your model, you wanted the input inter-arrival times to be exponentially distributed, and now you're verifying that the inputs are exponentially distributed, that you didn't accidentally type in the wrong thing. So what is the word we use for confirming that your code is correct based on the design that was in your head? And that's all I've got for you. So we'll see you on Thursday to wrap up the power analysis.